the research I conducted was on member inference and machine learning models. So machine learning and neural network models are inherently able to memorize data by virtue of the way they are trained and fit to the data. This memory leak, which occurs due to inference of whether a specific bit of information was included in the training set. So there's this, when you train data, the model has a better ability to predict the data that was in the training set, particularly in cases of overfitting. So based upon that, in essence, the model has memorized that data to a certain degree. And from that, we can infer what data was part of the training model, which gives us insights into many different things, such as, if we were doing some kind of disease screening on patients and we find somebody's personal medical data, we may be able to run that data against the model. And if it has a high confidence score, we could be pretty certain that that data was in the training model, and then that may be able to tell us a little bit about that person. And this is, especially dangerous if you look at people that are maybe in positions where that could be very detrimental to their position or their work, public figures, etc. You could look at things such as, maybe a model was trained on images of all the driver's license images in a state, but the model was meant to be able to pick up people that maybe have a criminal record, and those people had additional images in the training data, such as like the mug shots or something when they're arrested. Well, those people, if you go and take a model like this, you may be able to say that with a high confidence score, that person's image must have been in this training data set more frequently than just the person that has just their driver's license in there. And then you can start to infer information about that person, possibly that they had a criminal record. So there's a couple different ways to do that. Traditionally, the attack was done by looking at loss models. So you would take the loss metric of a model, and then you would look for, the training data, especially in the cases of a highly overfit model. When the data was in the training model, it would have a very, very low loss. And if the data wasn't in the training model, then it would have a very high loss. And you can see that demonstrated down below here, where, models trained on an image would be very low loss, high frequency in that area with a good separation between the images that were not in the training data set. And this is best case scenario when you look at a highly overfit model. Now, if they're not highly overfit, they're production ready, and they have maybe validation and testing scores that are equal to the training scores or higher, that overfitting is not likely to be as easy to look at and make this determination. And you'd see an overlap during these two distribution curves. But because of that, the LIRA attack, likelihood ration attack, was created. And this really gives you a likelihood score that something was in there based on prior knowledge of the accuracy of the model itself and the data that was in it. Now, this is extremely useful in some cases. One example would be a mortgage loan application that maybe is constantly in training mode. So you have the model, you're able to run data against it, get scores, and then this model is continuously trained, because when new applicants come in, the loan officers at work at the bank may update the records of approved, not approved, or some other data figures, and then the model continuously trains itself and gets better based on that training data. In this case, you would have some prior knowledge, and you would be able to see the change in the model, and this attack would work. But in a black box setting, you really don't have that ability to do so. And this is just an extremely difficult to pull attack to pull off, particularly because you need some prerequisite things to be in place that are outside the control of the attacker, such as having that information about an existing data set and how it's scored with accuracy to start with. So this project really focused on the first traditional method, but instead of looking at the loss, I'm looking at it from a purely black box perspective where I don't have any information on that. And all I can do is look at results and look at the confidence scores of the categories. So what I did to set this experiment up is I took and trained 3 different models using TensorFlow. I did transfer learning using the Inception V3 model, which is highly specialized model pre-trained on images. And then I added an additional global layer to summarize everything, and then 500 nodes at the end that represent 500 classification possibilities at the end. And that was it out of the box. It was pretty accurate. I trained it, and the 3 different models that I trained and saved were one on the full data set of images. The second model I trained on all of the images except for the African crowned crane. I left one image in there just so that the model would have that as a classification category that it could actually apply a prediction to, but I've removed all the other images. So there was not enough images to sufficiently train it and get any kind of accuracy. Really, that one image was just a placeholder. And then the third model I trained with TensorFlow differential privacy module, which is a library that adds noise to the actual training data so that you can't do inference because it puts enough noise in there that confidence level, confidence score drops a little bit. And then you really can't infer, well, hey, this was in the training data or it wasn't, based on how high the confidence score was every single time, because it's going to differentiate every time you run a prediction on it because of this privacy model, and it's going to be a little bit lower. So that inference is much more difficult. The data set I used was Kaggle. It was 100 bird species. This data set is updated very frequently. I think the last update was 17 or 18 days ago at the time of this recording, and they had 525 bird species. When I did it, it had 500 categories, so that's why I had the 500 nodes at the end of my neural network. So there's 500 possible categories of classification, and there were over 85,000 colored images processed at 225 by 225. So this data set was enormous for this project. It was over 2 gigabytes of data, and that really kind of gives you a realistic approach of how this may work in a production system. Right here is just an image, just a snippet of some of the images that were in the African crowned crane module itself. So for results, the first 2 models I have here, model 2, no privacy, but both models without the privacy, the first and second model, this is my validation accuracy. So close to 85%. And the training accuracy, was up there around 77, 78. I intentionally changed the training a little bit by taking the images and as part of the image generator, skewing them, rotating them, zooming in and out, basically adding that differentiation to the images so that I didn't overfit on the training data. Instead, I had higher validation scores, really trying to mimic a production setting. And I didn't train extensively. I did 12 epochs, and each epoch or each training run of 12 epochs took about 2.6 hours on these models. So I didn't want to spend all my time on training, given this is just a proof of concept, but I did want to have the accuracy sufficient enough that you could have confidence in the categorizations when they were correct, and you expected them to be, certain correctness. Now for the differential privacy library, I tried at least a dozen different times. I did a lot of hyperparameter tuning, and the best I could get was 0.006. So this was less than a random guess. This was completely useless. I had to throw it out of the experiment. The initial intent was to actually be able to do the inference and then run things through model 3 and hopefully demonstrate that with this noise added in the privacy library, I would no longer be able to infer the results. But this library just didn't work with such a large and complicated data set like this, doing a lot of research looking out there. While this is publicly available, open source, it's not quite ready for prime time commercial use or production use right now. A lot of people had problems with it, and it seemed like the only use cases where it was actually working were very simplistic, small data sets where people were just doing demonstrative purposes. and the models were extremely highly overfit. If they weren't really overfit, then people would lose too much accuracy for it to actually be productive. But for anything complicated, the results were people were getting less than 1% accuracy. So there's definitely some deficiencies and things that need worked out in this library before it's ready to be beneficial. So for my results, the inference did work. So for the first model, I was able to get a confidence score on par with the validation accuracy on my prediction of this African crowned crane. So it's important to note that when it's on par with the validation score, that's kind of your ceiling for potential. And that really is an extremely high confidence. That's the right one. And that can tell me that it's in the training model when it's hitting right with that validation accuracy. Now, if we were doing this without my knowledge of what those accuracy scores were, and I was just getting the accuracy 84, 85% on this classification, I would need to do something else to help me. So what I did was I trained the second model without those images, and then you can compare the two models and see what the classification score was. And in the case of the second model, it did not classify the African crowned crane correctly, and the confidence score for that was very low. And the reason why it didn't pick it with the right classification, but I still had a score, is the way the output of this model is it gives you a NumPy array of 500 numbers representing the 500 classification categories. And each single one gives you a confidence score, whether it's that classification or not. So something the model is very certain that it is not is a 0. Something it's very certain that it is would match roughly around your validation score, maybe slightly lower, slightly higher, but in that range of 84, 85%. And then you have to look at those results, that NumPy array, and match them with your folder structure in your training for the code that I wrote to actually understand them. I didn't do a printout here because, like I say, it's just a very large NumPy array with 500 items in it. It scrolls across the page, and it was very hard to capture and articulate for visualizations the way it was. If I was going to spend a little bit more time on this model, I would have went and built some kind of data frame that labels all the output and puts it in some kind of consumable format for presentation purposes. But given the time constraints, that didn't happen with this part of the experiment. The important thing was just getting the results. Like I mentioned earlier, Model 3 was just unusual. So, my results and my conclusion are that differential privacy measures don't work. They're just not suitable at this point in time to try to mitigate this type of attack. However, in conclusion, while member inference is a real threat, and I was able to prove that it does work, in its current state of maturity, they're really a lot better attack vectors using traditional hacking methodologies. So you could go out and do a data exfiltration, retrieve all the training data. Now you have 100% confidence of the data, what data was included in that training set, and there's no doubt to those facts. Whereas if you would do this attack even successfully, there's still a likelihood, and you're not with 100% certainty sure that this data was included in the training set. So really the traditional attack vectors where people do data exfiltration, data breaches, that's still really the best approach. And this isn't quite a huge threat just yet, but I'm sure as it matures, it will be much more of a threat and techniques get better. Hopefully by that point in time, some of these privacy libraries will have caught up and actually be effective. So the other thing I just wanted to demonstrate here really quickly, this is the bird species on Kaggle, so up to 525 already here. We have the training data, and this is the African crowned crane that I used. As you can see, every data category has roughly around 150 to 200 images in it. The one I left in just to keep the classification going was this image 79. As you can see, the head is pretty distinct but obscured by this background, so I didn't want to give the model any ability to train just on one image, and I picked this image intentionally. I look through, you got your 500 categories. Every set is pretty large, around that 150 number, and they're quite detailed images of these birds. So a pretty difficult model to train. So when you do have a high accuracy score, you can feel confident that that data was included in the set. And just looking at the code really quickly, I'm not going to go through everything, but I did want to just kind of point out that, you know, you can run the code two different ways, python.main-pred and a T, and that tells you to run predictions only, don't train the models. Without that left out, it's going to train the models. If you want to do the differential privacy and just train that model, then it's a -dp and a T for true there. And then those models are, you know, these flags here, so you can follow it in the code. I want to point out the exception v3, basically this pre-trained model. There's my global average pooling layer that I added in, and then my prediction layers, which is my 500 nodes of just a dense layer. That's my output layer matching the 500 classification. So several different flags in here. And here on the image data generator, this is where I was able to produce some noise and get the validation score up so high by doing some rotation on the images, doing some shifting, height shift, some zooming in. Horizontal flip I left out because that really skews the data with an upside down image and really brings accuracy out. And then I used fill mode narrows. So this gave me enough variation in the training data that I didn't overfit and the validation score stayed up. So that's the conclusion on how this works. And I made the code available. Thank you very much.